Okay, this video is to help you guys see where the special right triangles come from. I am using a different device than usual, and I am also using a different annotation tool, so hopefully this works out. Anyhow, let's consider a square. We know that a square is a four-sided closed polygon that has four congruent sides and it has four 90-degree angles. If I take this square and I cut it in half from corner to corner, I have two different triangles. I've got a triangle I'm going to use a dashed line to represent that. I've got a triangle here, and then also I've got a triangle here. And this is actually two 45, 45, 90 triangles. If we think about those whoops, I'm trying to make that smaller. These side measures are all congruent, so let's say they're x, just hypothetically. Then it's true that this is x, this is x. This is the measure of x, and this is the measure of x. Now we had two 90-degree angles that were also cut in half. So 90 degrees divided by 2 is going to produce a 45-degree angle. So that's pretty nifty. But anyhow, this is just one way you can derive a 45, 45, 90 triangle. And I'm going to take one of them and we're going to prove the ratio relationship between the sides. So I'm going to go ahead and copy this triangle down over here and get to work. So we know that those two legs are both congruent. I don't know the measure of those legs, so I'm just going to let them be represented by the variable x. We know that this angle on the bottom left-hand side of the screen, that's a 90-degree angle. We know that this angle up here is 45 degrees. And this angle down here is 45 degrees. So this is actually an isosceles triangle because we have our two sides congruent and those two base angles congruent. But anyhow, let's go ahead and do some math to figure out the measure of this hypotenuse. And we know to find a missing side of a right triangle, we can use the Pythagorean theorem. And I'm going to abbreviate this. It is a squared plus b squared equals c squared. You know, we have two rules that must be followed when using that Pythagorean theorem. Rule number one, you have to have a right triangle. Rule number two, little c must correspond to the hypotenuse. As far as a and b, it doesn't matter which leg you let correspond to a and which leg you let correspond to b. That doesn't matter, but little c has to correspond to our hypotenuse. So let's substitute in some variable values here. We're going to have x squared plus x squared is equal to, and our hypotenuse, we don't know what that is. I'm just going to actually leave it as a question mark for now. Some unknown measure squared. If I have 1x squared, let me change colors here. I have 1x squared plus one more x squared. I have a total of 2 x squareds, which is equal to some unknown value squared. Hopefully you remember, in order to eliminate that power of 2 from our unknown value that we're trying to solve for, we would take the square root of both sides of the equation. So taking the square root simplifies that power. What you do to one side of the equation, you have to do to the other. And then my properties of radicals, we know that we can actually split up this factor pair over here. We have 2 times x square roots of 2. This can be rewritten as the square root of 2 times the square root of x squared. And lo and behold, this radical is going to simplify with that power of 2. So that's going to be equal to our unknown value. And that's going to leave us with the square root of 2 times x being equal to that hypotenuse. Now the way this is written right now is incorrect. Technically we want to have x in front of the square root of 2. So we're going to have x square roots of 2 equals our unknown value, that is our hypotenuse. So that's really nifty because whenever we have a special right triangle that's 45, 45, 90, we know that this relationship exists. We know that the legs are both x. So we have two legs that are congruent, and the hypotenuse is the square root of 2. Oh wait, not the square root of 2, it's x square root of 2. Forgive me. Oh, I just erased everything. Let me zoom back in a bit. So let me restate that. Whenever we have a 45, 45, 90 special right triangle, we know that our legs are congruent and that our hypotenuse is going to be x square roots of 2. And this software is acting a little silly. But let's do a couple problems, or a few problems, using this concept. Okay, give me just a second. I'm actually going to go borrow some problems. Okay, so I went and borrowed some problems from the CUDA Math software that we use for additional practice at our school district. Anyhow, here the instructions state, find the missing side lengths, leave your answers as radicals in simplest form. These 4 problems are all 45, 45, 90 triangles. Anyhow, let's go ahead and solve some of them together. So, and remember, the entire time I'm doing this, I'm keeping in mind that with a 45, 45, 90 triangle, I know that my legs are going to be congruent. So I'm going to have 2 congruent legs, and then my hypotenuse is going to be x times the square root of 2. So I know that relationship exists. These first 2 problems are a little bit more challenging because I have my hypotenuse given to me first, but it's not that difficult. I know that my hypotenuse is equal to my leg times the square root of 2. I know that that exists based off this diagram over here. I know that my hypotenuse is 4 square roots of 2, and I don't know what my leg is. So x times the square root of 2. I'm trying to solve for x, and here x is being multiplied by the square root of 2, so to undo that multiplication, I am going to divide both sides by the square root of 2 to isolate x. On the left-hand side of the equation, you know, we have the square root of 2 divided by the square root of 2, so that's going to simplify to 1. And then 1 times 4 is just 4. So we're going to have 4 is equal to x. Now again, because this is a 45, 45, 90 triangle, I know that those 2 legs are congruent. So A equals 4 and B equals 4. Okay, let's go over here. Here my hypotenuse is 6 square roots of 2. I know that based off of this diagram, when I have a 45, 45, 90 right triangle, my legs are congruent. And my hypotenuse is going to be my leg times the square root of 2. So I know that my hypotenuse equals the leg times the square root of 2. We actually know what our hypotenuse is. It is 6 square roots of 2. So I'm substituting that in place of the hypotenuse label. I don't know what my leg is. I'm just going to say x times the square root of 2. And then to isolate x, we want to divide both sides by the square root of 2. Now these ones are working out really nice. it's not always so nice. Sometimes you have to do some further simplification because you might end up with the square root of something in the denominator, like the square root of 2, and then you have to rationalize your denominator. Anyhow, if we don't see one in the next couple problems, I'll force that to happen. I'll make an additional problem for us. But anyhow, we know that our legs, they're congruent, and they are both going to be just 6. Now, some kids are really good about just looking, and whenever your hypotenuse is something times the square root of 2, they just automatically see that leg value is whatever that whole number is times the square root of 2. Sometimes it's not so straightforward, though. Okay, so let's look at number 3. Here our hypotenuse is 9, and we're looking for our legs. Now, this one's not so straightforward, but we are going to pull in that same fact that our hypotenuse is equal to our leg times the square root of 2. We know the hypotenuse is 9, so let's substitute that in there. We don't know our leg yet. I like to use x for my leg because of that diagram that we made together. So anyhow, we're going to have 9 is equal to x times the square root of 2. Here, let's divide both sides of the equation by the square root of 2. And we see this one's going to require a little bit more algebra, but it's not bad. So we have 9 divided by the square root of 2 is x. Now, you can't leave that square root of 2 in the denominator, so we're going to rationalize this ratio by multiplying it by the value of 1. So the square root of 2 divided by the square root of 2 is what we're going to multiply it by. So we'll end up with, trying to change the color here, 9 square roots of 2 over the square root of 4. And we know that the square root of 4 is 2. So 9 square roots of 2 over 2 is the value of x. And x is the value of both of our legs in this problem. Let's look at number 4. Okay, with number 4, we have that hypotenuse. It's 2 square roots of 2. If you notice the patterns, you could just say that n is 2 and m is 2. And we've already worked a couple out using the algebraic strategy. Here, I'm just going to go ahead and use that pattern to move on. Okay, another special right triangle that we have is our 30, 60, 90 triangles. And they come from an equilateral triangle being cut in half. So let's talk about that. An equilateral triangle is a regular polygon with 3 sides. And again, by definition of regular, we know that those 3 sides are congruent, and then also the angles are congruent. So if we have an equilateral triangle, we know for sure, I'm trying to change this weight down. Let's do 5. But if we have an equilateral triangle, then we know that each of these interior angles has a measure of 60 degrees. It just has to be so. Now here, this gets cut in half, just like we did with that square. So I'm going to drop an altitude. And if I cut this in half, you know, this altitude is going to be perpendicular to the base. So I'm going to end up with a 90-degree angle here. I'm having a hard time drawing. Okay, and I'm going to actually take this portion of the triangle out so we can look at it by itself. You know, half of 60 is 30. Now, an equilateral triangle, we know that all the side measures are the same. So we could say this side measures x, this side measures x, and this side measures x. And we can actually take that information and transpose it over here to label the side measures of this 30, 60, 90 triangle. I know that this right here is going to be x, and then this base, the side that's straight across from that 30-degree angle, that's going to be half of x. Now, usually this is where students kind of start to panic in my classroom, and so they don't like to work with fractions. And so I ask them, you know, what is a way we can avoid working with fractions here? And some students or some class periods are able to come up with a way on their own. Others need more help from me. But I want you to pause and think about, is there a way that you could force this fraction to have not happened by how we've selected our original side measures for this equilateral triangle? I'm going to assume that you've already paused the video, you've attempted guessing what you could do. But if we know that we're cutting this in half and we're ending up with this 1/2 x, the best or easiest way to avoid working with fractions is to, instead of giving your equilateral triangle side measures of 1x, give it side measures of 2x instead. Okay, so scale it up. It's still an equilateral triangle, and we can still cut that in half. You know that half of 2x is 1x. So that just lets you work with whole numbers, which, I mean, for some reason seems to be friendlier for most students that I've encountered. Okay, and then from here, let's go ahead and use the Pythagorean theorem to solve for this missing side. I'm going to use a question mark again to emphasize on that side there that we're missing. And this is the long leg. It's another thing I like to reference this as, is the long leg. We have our hypotenuse, and we have our little leg. Okay, now the Pythagorean theorem, it's a squared plus b squared equals c squared. We're going to use it just like we did last time. A and b correspond to either of your legs. It doesn't really matter which one's which. And then c has to correspond to your hypotenuse. I do prefer to let my unknown value be or correspond to a, so that way it's towards the front. Again, it doesn't matter though. You can do whatever you want. But I am going to place a question mark in place of a here. So I have question mark squared plus b, which is going to be 1x squared. It's equal to c, so that'll be 2x squared. So we're going to have our question mark squared plus x squared is equal to 2x times 2x is 4x squared. My goal is to isolate that unknown value, that question mark. So we need to subtract 1x squared from both sides of the equation. So we have our question mark squared. You know, 1x squared minus 1x squared is 0. So our question mark squared is equal to 4x squared minus 1x squared leaves us with 3x squared. And just like earlier, we need to isolate that unknown value, that question mark, and it's being raised to the power of 2. To undo that power of 2, we are going to take the square root of both sides of the equation. So our question mark is equal to, and using properties of radicals, I know that I can split these factors up. I can have the square root of 3 times the square root of x squared, so I am going to go ahead and do that here. And the reason why I'm doing that is because x squared is a perfect square, meaning this radical, the square root, is going to simplify that power of 2. So our unknown side is equal to the square root of 3 times x. And again, just like with our 45, 45, 90 triangle, we're going to rewrite our solution as x square roots of 3. So all of that algebra is necessary so we can prove the relationship between the sides of our 30, 60, 90 triangle. We know that our hypotenuse is twice as long as that little leg, so it's 2x, and our little leg is just 1x. And then using the Pythagorean theorem, we were able to prove that that long leg is x times the square root of 3. Okay, I'm going to pause this, and here in a minute I'm going to solve some problems. Okie doke. So I went and took some more problems so we can work out some scenarios involving 30, 60, 90 right triangles. And again, keep in mind, this entire time as I move through these problems, I'm going to think about the relationship that I'm aware of when working with this special right triangle. For starters, I want you to remember that we did begin with an equilateral triangle that was cut in half. We dropped an altitude that was perpendicular to that bottom base of the triangle. So when that happened, we ended up with a nice right triangle. I took away half of it. You can see the little red arrow going to it. And we know that that bottom base to our right triangle is half of the hypotenuse of this right triangle. Now again, if you're curious about why we are working with the 2x instead of the 1x, just remember, or maybe rewind this video, when we had the 1x, we ended up with a fraction, which isn't that big of a deal. It's actually really helpful and connects to the unit circle. That's something that some of you will learn about in your future years of study here. But anyhow, most people try to avoid working with fractions. So we worked around that by scaling our equilateral triangle up. So we dilated it by a factor of 2. So we multiplied each of the sides by 2 and then cut that in half. And half of 2x is 1x. We performed the Pythagorean theorem to solve for that long leg. And we found that that long leg is actually x times the square root of 3. Another thing that is safe to note is that there is a relationship between angles and the sides opposite of them. So our angle that is the smallest is going to be straight across from the side that is the shortest. Our angle that is the medium length or medium measure is going to be across from the side that is medium length. And our angle with the largest value, so like 90 degrees in this case, is going to be straight across from the longest side in our right triangle. So that's another helpful key fact here. But we end up with this ratio of, we've got 1, well, if I could draw, that'd be great. There we go. Of 1, 2, square roots of 3. Ooh, that looks a little funny. Okay, so 1, 2, square roots of 3 to 2 ratio, and that's just, the connection between our side lengths here. But anyhow, so again, the entire time as I move through these problems, I'm going to keep this in mind. And before I even start, I just want to make something known to you. You have to know what your little leg is in order to find the hypotenuse. Or you have to know what your little leg is in order to solve for the long leg. So sometimes you'll be given a hypotenuse measure, but you'll be asked to calculate the length of a long leg, or vice versa. And I want you to keep in mind that each time that happens, you should always go back and determine what is the value or the length of that short leg, that little leg first, so then you can scale it back up. So I like to write down a few formulas. I know that my hypotenuse, and this is for our 30, 60, 90 triangles, I know that my hypotenuse in this case is equal to 2 times the little leg. Okay, so I know that that's true. And then another thing that I know is that my long leg is equal to my little leg times the square root of 3. And so that's just some, relationships that I can deduce by looking at this diagram. So these are 2 formulas, if you would like to say, that you need to keep close to heart. So let's scoot on down over here. Let's look at number 5 here. I know what my little leg is. So here is my little leg. I'm just going to call it little. Here's my long leg, and I'm just going to call that one long, and here's my hypotenuse. I know that my long leg is equal to my little leg times the square root of 3. Okay, so I know that my long leg n is equal to 6 square roots of 3, because here's a 6. I understand my L and E, they kind of look like a 6, so let me draw that a little bit better. Well, I'm erasing all kinds of things. There we go. And I know that my hypotenuse is 2 times my little leg. So my hypotenuse M here is 2 times 6, which is 12. And we're done. Okay, let's look at number 6. And I apologize for the noise. We are home on, today's a snow day for our school, so my dog is chowing down on her kibble. She's not too far from me. Anyhow, here I've got my little leg. Here's my long leg. Here's my hypotenuse. I know that my long leg is equal to my little leg times the square root of 3. Well, here my little leg is 3/4. So my long leg y is 3/4 times the square root of 3. And I'm done. My hypotenuse is 2 times my little leg. So in this case, I'm going to have 2 times 3/4, which is 6/4, and that simplifies down because 2 times 3 is the same thing as 6, and 2 times 2 is the same thing as 4. And these 2's are going to simplify, and that reduced fraction is 3/2. Now I just showed a whole lot of work for that. If you can do it in your head, by all means have at it. Where you guys have calculators you can use. I'm not testing you on whether or not you can simplify fractions. It is very helpful though, because next year, whenever you're studying Algebra 2, you want to make sure you understand why fractions are simplifying, especially whenever we're working with rational polynomials and needing to simplify them. Anyhow, let's look at number 7. So with number 7 here, I don't know my little leg, but I do know my hypotenuse. And I just want to remind you that your hypotenuse is 2 times your little leg. And I'm just going to say little here to kind of abbreviate it. So I can actually use this formula in order to find the value of my little leg. And again, I'm sorry about my writing. I don't have a stylus for this new device that I'm using, so I'm having to use my index finger, and it looks a little not the best. Anyhow, so my hypotenuse here, I know that is 4 square roots of 5, and that's equal to 2 times my little leg. That L did not pick up. So if I'm trying to solve for my little leg's measure, it's being multiplied by 2. I'm going to need to undo that multiplication. That inverse operation of multiplication is division. So I'm going to divide both sides of the equation by 2. Now 4 square roots of 5 divided by 2, we can simplify this because 4 is the same thing as 2 times 2. So we're going to have 2 times 2 square roots of 5 divided by 2 is equal to our little leg. And these 2's here are going to simplify. So we know that 2 square roots of 5 equals our little leg. So our little leg is 2 square roots of 5. I'm kind of circle that there. Now let's go ahead and solve for the long leg. We know that our long leg, and I'm going to write down that little formula. Well, we know that our long leg is equal to our little leg times the square root of 3. And we're trying to figure out what that long leg is. We know that our little leg is 2 square roots of 5. Oh gosh, this is looking terrible. So we're going to have 2 times the square root of 5 times the square root of 3 is the square root of 15. And that radical does not simplify, so we are finished here. Oh my goodness, it looks awful. But anyhow, x is 2 square roots of 15, and y in this case is 2 square roots of 5. So this did require a little bit more work. Let's do another one. I'm not going to do all of these. I'm trying to see which one looks more challenging. Actually, I think I'm going to do 2 more. I think I'm going to do number 9 and number 12. Yeah. So let's do those. So we're going to do number 9. Here I have my hypotenuse, and I just want to remind you that my hypotenuse is 2 times our little leg. Well, I know the hypotenuse is 8 square roots of 3 over 3. So we're substituting that in place of our hypotenuse. It's still equal to 2 times this the little leg. And here, because I have a fraction on the left-hand side, I really am not going to, I don't want to go and divide by 2 because then we have to multiply by the reciprocal, and that's just extra work. Instead, I am going to go ahead and just multiply by the reciprocal. I know that I want this 2 to simplify to 1, and so if I multiply both sides of the equation by the reciprocal, that simplification is going to occur for me. So I'm going to multiply the right-hand side by 1/2 and the left-hand side by 1/2. And again, the reason why I'm choosing to go ahead and just multiply by the reciprocal is because if I were to write divide by 2 on both sides of the equation, we're going to have to anyways take that fraction and then multiply by the reciprocal. So I'm just kind of saving myself some work. Anyhow, my numerator right here, I'm going to have 1 times 8 square roots of 3. That's just going to be 8 square roots of 3. My denominator right here, 2 times 3 is 6. Okay, that's going to be equal to. Here, if I were to have 1 times 2, that's just going to be 2 over, and this 2 times, there's an understood denominator of 1. So it's 2 over 2, which is just 1. Now I am showing every single little step. Let's go ahead and keep simplifying this though. Over on the left-hand side, I have 8 square roots of 3 divided by 6. 8 and 6 both share a greatest common factor of 2. So let's break it down. And I'm going to show you guys that GCF is 2. So 2 times 4 is the same thing as 8. And 2 times 3 is the same thing as 6. I'm going to switch colors again to write everything else out. Over here on the right-hand side of the equal sign, 2 divided by 2 is 1. So that's going to simplify to 1, and then we've got our little side all by itself. Now these 2's are going to cancel. I'm going back to the left-hand side, and again, I'm showing y'all every single little step. So that way, if you're struggling with some of that pre-algebra stuff, hopefully it helps for you guys to see it again now that you're older. So our numerator is 4 square roots of 3, and that is divided by our denominator of 3. And that is the measure of our little leg. So our little leg is y. So right here, it's going to be 4 square roots of 3 divided by 3. And then our long leg, we know that our long leg is simply our little leg times the square root of 3. So we are going to have, and I'm going to actually bring this way over here because I don't have a lot of space. So our long leg is equal to our little leg times the square root of 3. I don't know why my LEs, they keep looking like 6s. I guess because I'm not lifting up. Anyhow, we're trying to figure out what that long leg is. We know that that little leg is 4 square roots of 3 thirds. It's being multiplied by the square root of 3. It is understood that that square root of 3 here has a denominator of 1. So we're going to multiply straight across. we have 4 times the square root of 3 times the square root of 3 is the square root of 9. 3 times 1 is 3. So our long leg is equal to 4 times, well, the square root of 9 is 3. All that's divided by 3. I could multiply 4 and 3 together to get 12 and then simplify that. 12 divided by 3 is 4. But instead of doing that, I am going to go ahead and just show that, hey, anything divided by itself will simplify to 1. So I know that that long leg is simply 4. Now my notation is not appropriate here, with me just saying long and little. Hopefully it sends the message clear enough though. And I was going to do number 12, but I didn't realize the time. I'm actually going to go ahead and stop this video. If you need to see more examples of 30, 60, 90s worked out, feel free to look on YouTube. There's a lot out there. Also, I can assign some, or actually I will assign some extra practice in Delta Math. So if you want to sign into Delta Math just to practice these skills, you can. Understanding your special right triangles is so helpful. It makes your life easier. It really does. Okay, have a good day.